Hi, in this session we are going to discuss the tunneling phenomenon, especially in the case of a barrier potential and also the linear harmonic oscillator. So in the case of the barrier potential, the only important kind of problem is to find the tunneling probability, so we will be looking into that, whereas the linear harmonic oscillator is very important, right? Be it in the case of examinations or even in the whole world of theoretical physics, this harmonic oscillator has a very important role, right? There's a lot of things we can learn from harmonic oscillator. So we'll be dealing with harmonic oscillator in more detail, and also we'll be trying to solve as many problems as we can from a linear harmonic oscillator. So in this case we are looking at the finite barrier potential, all right, finite potential barrier. In this case the specification is given like this. For x less than 0, the potential is 0, the potential energy is 0. Between 0 and a, right, between 0 and a, it has a finite height, v0, all right, and beyond that it's 0, right? And especially we can discuss two cases, e greater than 0 and e less than 0. We'll be focusing on e less than 0. We'll be discussing on, sorry, not e less than 0, e less than v0. It means that the total energy of the particle is less than the height of the potential barrier, all right? We'll be discussing that case. That's where we see some classically non-occurring phenomenon called as tunneling, all right? So we'll be focusing on e less than v0 case only. So here is the representation of that potential. Here it has a height v0. Here we have drawn the energy line, all right? This line represents the energy of the incoming particle, or the total energy of the incoming particle. So you can imagine some particle with this energy coming from the left and encountering this height, okay, this potential of height v0. Right, it's like, you know, running along a free path and encountering a wall in front of you, right? So if you don't have enough energy, usually you cannot get over it, right? That's the classical thing we believe. I mean, that's the classical behavior, all right? But quantum mechanics says something different, all right? Even if the particle has does not have sufficient energy to cross the potential barrier, you see that the energy line is below the v0, okay? This, all right, so then what happens? All right, so we can write the wave function in the three different regions, all right? In this case you have got an incoming plane wave. Plane waves represent free particles, all right, and we also have a reflected part here, and inside we have got these two parts, and outside there's an outgoing part. That's all, okay? That's all we have here. We won't go into the details, but the solution will be of this form. But the important thing here is that we can calculate the tunneling probability, all right? Quantum mechanics says that there's a non-zero probability that a particle of energy less than v0 can actually cross this barrier, all right, without enough energy, without overcoming the potential, all right? That's known as tunneling. So how do we know this? Because quantum mechanics predicts this, all right? Which means that the Schrödinger equation in this situation actually predicts that the particle can actually, there's a small but non-zero probability that the particle can actually cross to this region, even though it does not have enough energy to overcome the potential the potential barrier, all right? So it's almost like you keep running towards a wall, and you hit the wall many times, and if you keep on doing this for a very long time, all right, for a very long time, there's a small probability that one of these times you will actually end up on the other side of the wall, all right? We don't see this in the microscopic world because the probability is so diminishingly small, but in the microscopic world this happens all the time, all right? For example, alpha scattering is an example for a quantum mechanical tunneling. Okay, all right. So we'll just calculate the tunneling probability here. We can find the tunneling probability by taking modulus E square divided by modulus A square, right? So what's modulus A square? It's actually the amplitude of the walls which are, amplitude of the particles which are approaching the wall from this direction. Okay, that's A, all right? And E is the amplitude of the waves which are traveling, or amplitude of the particles which are traveling in this direction, all right? Now what's the probability that the particle represented by A e raised to I k1x end up on the other side of the potential barrier, all right? So which means that you are actually asking of all the number of particles. You imagine that you are hitting this with a large number of particles, all right? What fraction of these particles will actually end up on the other side? That's a question, all right? To get that fraction, you take the total number of particles which are traveling towards the wall and what fraction of them have reached on the other side, all right? This is the probability for tunneling. We normally write it as T. All right. So quantum mechanical analysis shows that the tunneling probability is given by this equation. All right. Here K2 is square root of 2m V0 minus E divided by h cross square. All right. K1 is simply square root of 2me divided by h cross square. All right. Sometimes this K2 is also denoted as beta. Right. Sometimes in the problems this K2 is also denoted as beta. Maybe it's more of it's more used, all right? The beta term is actually reserved for this in many textbooks, okay? All right, so this is the equation for the tunneling probability. So if you are asked to find the tunneling probability, it's just a matter of applying this formula, all right? Applying this equation. Given all the variables we need the width here. A is the width of the barrier. But this can actually be approximated, all right, when for large A, all right, for large A, which is the case we'll be seeing most of the times, this can be approximated to simpler formula. I think this is the one we will have to memorize and we'll be using it in solving problems, all right? It's 16e V0 minus E divided by V0 square e raised to minus 2k2a. All right. Now it can further be approximated, all right? Even if A is huge or something, we can further approximate this as T is equal to e raised to minus 2k2a. All right. Sometimes this formula is sufficient. You can look at the problem and decide which formula is more suitable. So I want you to memorize these two formula, which should suffice for us to solve most of the problems that appear from this section. All right. So this is the representation of this. Here you have an incoming plane wave and then there's an exponentially, all right, almost exponentially decreasing. So in this case, it's actually an exponentially decreasing thing, all right, and then again a plane wave on the other side, all right. It's exponentially decreasing. This means that when the width of this potential well increases, all right, when the width of this potential well increases, this tunneling probability decreases drastically, all right. If the width increases, the tunneling probability decreases. Also, we see that if the height of the potential barrier increases, all right, if the height of the potential barrier increases, that means that K2 will increase, and also then the tunneling probability is low. Okay, so tunneling probability is quite high if E approaches V0. Right, if E approaches V0 and A is not very large, all right, A is not very large. Okay, I mean this much is enough for us to solve problems which are relevant to our aim of competitive examination. So let's look at some problems now, all right, a couple of problems at least here. So this is the kind of problems that we expect from this part. Calculate the percentage transmission, all right, there was the percentage transmission of an electron beam of energy 3 electron volt when incident on a potential barrier of height 4 eV, all right, and width 20 angstrom, all right. So we are given everything, all right, we are given the energy, here, energy of the particle, we are given the height of the potential barrier, we have also been given A, all right. So you just blindly apply to this formula. You have to calculate beta. Okay, here beta is given like that. As I said, beta is K2, and then you just apply it, do the calculation, and you'll get this answer. Okay, we are asked to find the percentage of transmission. All right, so we multiply by 100 here, and we see that there's a very small percentage of particles which actually will get transmitted to the other side. All right, so you can actually do this calculation. And we first calculate 2 beta A here, all right, then you substitute it in here, and then you can use the calculator and do this, all right. Now, sometimes it will suffice for you to calculate just e raised to minus 2 beta A, all right. So try with both these formulas. I want you to try this, an exercise for you, okay. We won't spend much time on this, is an exercise for you. So I want you to try using this formula and simply e raised to minus 2 beta A, all right, and see how much of the difference there is, all right. So if there is no difference in by an order of magnitude or so, you can use this simple formula, all right. Okay. Here is another problem which is also historically important, because Gamow and Teller actually explained alpha decay using this tunneling phenomenon in quantum mechanics. So here we have got an alpha particle which is trapped in a nucleus of radius. The radius of the nucleus is given. What's the probability that it will escape from the nucleus if its energy is 2 MeV? Alright, the energy of the alpha particle is 2 MeV. The potential barrier at the surface of the nucleus is 4 MeV. As we said, the energy of the particle is less than the height of the potential barrier, and the mass of the alpha particle is also given. Alright. Now, it's an important thing that you remember the width of the potential barrier is taken to be the diameter of the nucleus. It's to be taken as the diameter of the nucleus. So, it will be twice 1.4 into 10 raised to minus 15 meter. So, please do the calculation and see if you get this answer. Alright. Now, if I am wrong with this answer, you will find out by calculating. Alright. So, I think that's the kind of problems that we expect from the tunneling part. We won't spend much time into this. We'll move on quickly into another very important session, the linear harmonic oscillator. Okay, so the quantum mechanical linear harmonic oscillator, of course. All right, I repeat, this is very important both in physics and in examinations. All right, so we'll be spending some amount of time on this particular problem, trying to solve more problems. All right, we can look at the old question papers and get problems from there and solve them. Right, but we can always expect a question from linear harmonic oscillator, the quantum mechanical case. Okay. Now, without going into much details, we can look at the Hamiltonian. The Hamiltonian is p square by 2m plus half m omega square x square. Alright. So, you see that this is the same as the classical mechanical Hamiltonian. We can check this is the same as the classical mechanical Hamiltonian, except that instead of these operators, we have normal functions. That's all. Alright. So, the Hamiltonian can be directly found from the classical mechanical thing by changing the functions to operators. Alright. And the first thing we do is to find the analytic solution. All right. Obviously, we solve the eigenvalue problem. H psi is equal to E psi. All right. That's the eigenvalue problem that we solve. In this case, the solution is a bit more involved. All right. It's not quite straightforward, but mathematicians have already found certain differential, played with certain differential equations, and we can actually change this. We can actually change this into a non-standard differential equation, and then we'll get the solution. All right. So, we won't go into those details, but the final eigenvalues are n plus half h cross omega, and n here is taken 0, 1, 2, 3, etc. Okay. N equal to 0 is a possible state of the system. Okay. Now, the energy eigenfunction is given in terms of the Hermite polynomial. All right. Hermite polynomials. So, the trick here that we do is actually we turn this into a differential equation. We can actually make some do some manipulations and make it look like a Hermite differential equation, and then the solution is obviously the Hermite polynomial. All right, this is the normalization factor. You have got e raised to minus x square divided by 2x square, and hn here is the nth order Hermite polynomial. Alright. Now, it's a good thing to remember these dependencies, but you may not be able to keep in memory all these things. Usually, such wave functions can be given, but I want you to remember the ground state wave function. Alright. I want you to remember the ground state wave function. So, normally when the problems are asked, all right, which means n equals 0, when problems are asked, either they give these wave functions, all right, otherwise you are supposed to remember the ground state wave function, all right, just like you are supposed to remember the wave functions of the square well, infinite square well potential, etc. Here you are expected to remember the ground state wave function, all right. They may say something like a particle is in the ground state of linear harmonic oscillator potential or something like that, all right. So, for that you see that for n equal to 1, h0 of y is equal to 1. So, it gets further simplified in this way, right. You just put n equal to 1 and then this gets simplified, and the ground state wave function is simply psi 0 of x is equal to m omega divided by pi h cross whole raised to 1 by 4 e raised to minus m omega x square divided by 2 h cross. All right. So, please remember this, study this, okay, memorize this. All right, you will need this, and you remember that this is a Gaussian. All right, this is known as this is of the form of a Gaussian function. This is a Gaussian function. It's of the form e raised to minus x square by alpha or something like that. All right. So please remember this ground state wave function. Now that was the analytic method, but there's a much more elegant and important method to solve the harmonic oscillator problem. It's known as the algebraic method. Okay, so let's go into the algebraic method. This is also very important, and when solving most of the problems, we can easily solve problems using the algebraic method. All right, using the wave function and integrating etc. may take a lot of time, and you may get integration wrong, or you may not know how to integrate. But in this algebraic method, there are certain rules that you need to remember, and if you remember these rules, the calculations are often very straightforward. All right, very straightforward and easy. So let's look into this algebraic method. So we start with the Hamiltonian here. You might have already studied this. I'll just repeat it for refreshing your memory. That's the Hamiltonian. It's p square by 2m plus half m omega square x square. Let's make it dimensionless and write it as p square by 2m h cross omega plus half m omega x square divided by h cross. All right. Now it can be written into a more instructive form by pulling this 1 by 2m h cross omega outside, and you get it of the form p square plus m omega x whole square. All right. So this is Hamiltonian. H is equal to 1 by 2m h cross omega multiplied by p square plus m omega x square. So this simply looks something like x square plus y square. All right, x square plus y square. All right. So if you have something of the form x square plus y square, if it's not an operator, if these are functions, then we can normally write this as x plus iy multiplied by x minus iy. Right. Here we cannot directly do that. Okay, because these do not commute. All right, operators do not commute, but we can try something like that, and we introduce two operators here. All right, we introduce two operators. You see that we introduce two operators, like this is square root of 1 by 2 m h cross omega. Okay, so we introduce two operators, and this 1 by 2 m h cross omega we divide to these two operators. For each operator we have a factor square root of 1 by 2 m h cross omega. All right, and we write it as just like we wrote x plus iy, just like we usually write x plus iy here, we write m omega x. All right, so here we have got m omega x whole square. So we write m omega x plus ip and m omega x minus ip. Okay, now you can also solve these equations, these two equations, to obtain x and p from in terms of a and a dagger. All right, we call them as a and a dagger because obviously you see that this a dagger is the Hermitian conjugate of what we defined as a. All right. Now it's also useful to write this x and p in terms of a and a dagger. That's what we have done here. All right. So the square root does not extend up to here. This is a small typo. I'll correct it in the notes. This is actually square root of h cross divided by 2 m omega and a plus a dagger. All right. So that's x and that's p. All right. Okay, now we are ready to get started, but we cannot simply write the Hamiltonian as a dagger. All right. Here we said that if you have something like x square plus y square, we can write as x plus iy multiplied by x minus iy. But simply we cannot, this Hamiltonian we cannot simply write it as a dagger or a dagger a. All right. We cannot simply do that because operators are a bit subtle. They don't commute. Right. So we cannot add terms which are multiplied in the opposite order, but still we can try and we can find the Hamiltonian in terms of a and a dagger, and we see that the Hamiltonian is h cross omega a dagger a plus half. All right. On the way, using the fundamental or the canonical commutation relation, this is known as a fundamental commutation relation or the canonical commutation relation, which is x with p is equal to ih cross. We have seen this. All right. So from this we can obtain the interesting commutation relation that the commutator of a with a dagger is 1. All right. Please remember this. All right. The commutator of a with a dagger is 1. All right. So most of the things that I am going to say in this session you have to memorize. All right. So the Hamiltonian becomes h cross omega is equal to a dagger a plus half. Now this a dagger a has a nice form. We'll simply write it as a new operator n cap. So h cross omega n cap plus half. All right. And what about this n cap? What about this n cap? We see that this n cap actually commutes with the Hamiltonian. All right. This n cap actually commutes with the Hamiltonian. Right. This means that the Hamiltonian and whatever this operator is n cap, we'll call it the number operator, right, for reasons that will become clear later on. Right. We see that they commute, so they have a common set of eigenstates. Right. So these eigenstates will simply denote it using the eigenvalues of n cap. All right. The eigenvalues of this n cap, we'll write it as small n. All right. So now our energy eigenstates are denoted by n inside a ket. All right, n inside a ket, a small n inside a ket. These are simultaneous eigenfunctions of h and n. Yeah, because we have seen that if you have commuting operators, they have a common set of eigenvectors, common set of eigenstates, common set of eigenvectors, right? Okay. Now, this means that n cap acting on ket n is nn and h cap acting on n is En. This is the energy eigenvalue. Energy eigenvalue. Right? So you see that the energy eigenvalue is actually determined by this n, which means that if you know the eigenvalue of capital N, you also know the eigenvalue of energy, obviously. All right. All right, and also we already know what this eigenvalue. It's n plus half h cross omega. It's n plus half h cross omega. Okay. Now this A and A dagger, right? This is known as dagger. A and A dagger are known as ladder operators, all right? A is known as the lowering operator and A dagger is known as the raising operator, all right? Why do we call it as a raising and lowering operators? Because suppose you look at the state An. So we know that, right? We know this thing. We know that if the particle is in the state n, ket n, a state denoted by ket n, then it has an energy En, right? Where En is n plus half h cross omega, all right? What happens to a particle in the state An? Okay, if there's a state which is, right, An, let's say this is n prime is equal to A cap acting on n, what's the energy of that? Let's check that thing, all right? Let's check that thing first. So you see here that h cap acting on the state An, we see that it's En minus h cross omega multiplied by the same state. All right, so this is clearly an eigenvalue equation. This is clearly an eigenvalue equation. This means that if the state n has eigenvalue En, then the state An has the energy eigenvalue En minus h cross omega. All right, so what has A done to this state n? It has lowered its energy by a unit, all right, h cross omega. Right, it has lowered the energy by a unit h cross omega, okay, unit of energy which is h cross omega. And that's the basic unit of energy in quantum mechanics. So it's En minus h cross omega A cap n. Also we see that if A dagger acts on this state, what happens is that its energy goes up by 1 unit. All right, for this reason we call A as the lowering operator and A dagger as the raising operator. All right, it's also sometimes called the annihilation operator. And this as the creation operator. All right, that's a term that will be used in quantum mechanics. In quantum field theory, you will see that this kind of manipulations have great importance in quantum field theory if you ever study quantum field theory, but it's a good problem to study. Right? And also we see that the states are normalized. We can construct these states as normalized, and the normalization we write it as if n with m is equal to delta m, nm. This means that 1 with 1 is equal to 1, but 2 with 1 is equal to 0, etc. All right, that's the normalization. These are the things we need to remember to solve problems. We need to remember a few more things. The normalized state after raising and lowering, all right? So what happens? We know that the energy goes down by 1 unit, okay? But what happens? How do you normalize the states, all right? It can be seen that the normalization goes like this. An, okay? A acting on n goes to a state n minus 1. Right, n minus 1 is the state with 1 unit less energy, all right, and the normalization factor is square root of n. Similarly, it can be found that A dagger n gives you n plus 1, the state n plus 1. The next state, the state with energy which is higher by a factor, higher by a unit energy, h cross omega. All right, and the normalization factor is square root of n plus 1. All right, as I said earlier, these are the things you have to remember to solve problems. It's not very difficult to remember, so please try to remember these things. Now, if you have one energy eigenstate, then all other states can be obtained by consecutive applications of raising and lowering operators. All right, if we know one energy eigenstate, all right, if we know one energy eigenstate, you can find all the higher energy eigenstates by consecutive application of the raising operator. Similarly, if you know, you can also find the other lower energy eigenstates by consecutively applying or by successively applying the lowering operator. Alright, now we call one state by the vacuum state. Alright, this is the vacuum state. This just means the ground state. Alright, the lowest energy state. Lowest energy state. Alright, so we start by the assumption that there indeed is a lowest energy state. Alright, there indeed is a ground state. Alright, we'll denote it by n equal to 0 state. Alright, obviously we have seen that En equal to n plus half h cos omega. N equal to 0 corresponds to the ground state. Alright, but this means that if it's the ground state, you cannot go further down. Alright, if you are on the ground state, you cannot go further down. There are no states with lower energies. That's what we mean by ground state. So we can define the action of a cap, the lowering operator, on the ground state as a cap acting on 0 is equal to 0. Alright, it takes you, there are no states below that. Alright, there are no states with lower energies. That's what it means. Alright. Okay. Now, yeah, this is the lowest energy state. Now, once you have the ground state, you can find all the other eigenvalues and eigenvectors by successive applications of the raising operator to the ground state. Okay. Alright, that's the end of the analytical thing. We'll just discuss the three-dimensional harmonic oscillator, just the details that we need before going into problems. Alright, in the three-dimensional harmonic oscillator, obviously we just add n plus half from each dimension. So it's nx plus half, the total energy, h cos omega, plus ny plus half, h cos omega, which means that you have got a harmonic oscillator which can oscillate in all three directions. Alright, so these three directions are independent, so we can take the energy in each direction and add them up. Alright, so the total will give you nx plus ny plus nz plus 3 by 2 h cos omega. Alright, now this is the case if the harmonic oscillator is isotropic. Alright, in some cases the potential or the system may have a direction dependence. Alright, it may not have the same properties in the x and y directions, and in that case it becomes slightly more complicated, which means that you have to find you may not be able to write it in exactly this form. Alright, you may not be able to write it in exactly this form. This is the case of an isotropic harmonic oscillator. Okay, isotropic harmonic oscillator. There is also an anisotropic harmonic oscillator, for which you have to simply be a little bit more careful. Alright. Now for simplicity, let's write nx plus ny plus nz is equal to n. Okay, nx plus ny plus nz. Let's denote it by n. Then E can be written as n plus 3 by 2 h cross omega. Alright. Now there is this formula for the degree of degeneracy. Right? How many states are there with a given energy? Right? In three-dimensional harmonic oscillator, you will see that there can be more than one state with a given energy, and the degree of degeneracy, it's actually obtained from number theory and all that. But the final answer for the degree of degeneracy is very simple. It's n plus 1 multiplied by n plus 2 divided by 2. That's the degree of degeneracy. All right. So sometimes problems have been asked to find the degree of degeneracy. You just apply this formula. All right. These are things, again, you have to keep in mind. Right? It's not very difficult to remember. It's simply n plus 1 plus n plus 2 n plus 1 multiplied by n plus 2 divided by 2, where this n is actually nx plus ny plus nz. That's all. Let's do a problem here. Find the number of possible eigenfunctions for a three-dimensional harmonic oscillator if the energy of the state is 7 by 2 h cross omega. Alright, it's 7 by 2 h cross omega. We are asked to find the number of possible eigenfunctions, alright, which means that we are asked to find is the degree of degeneracy. Okay, how many eigenfunctions are there corresponding to this particular energy? Right. So we see that for three-dimensional harmonic oscillator, the energy is given by n plus 3 by 2 h cross omega, which is equal to 7 by 2 h cross omega. From here, we see that n is equal to 7 by 2 minus 3 by 2, which is equal to 2. All right, which means that nx plus ny plus nz is equal to 2. Right. Now, if you look at the degree of degeneracy, it is n plus 1 into n plus 2 divided by 2, which is equal to 6. Right. So you can also check this in a different way. If nx is equal to, you can actually count the number of states. All right. Try counting the number of states to get the same result. We'll just use this formula to get the final result, which is equal to 6. All right. Let's do another problem. Find the energy of the first excited state of a particle in a two-dimensional potential, half m omega square x square plus 4y square. All right. So here we see that this is actually an example for an anisotropic harmonic oscillator because it has different properties in x and y directions. All right. So we need to find the first excited state. So let's see if we can write it in a more enlightening form. We write v is equal to half m omega square x square plus 4y square. Fine. So this we can write as half m omega square x square plus half m 2 omega square y square, right? Because this is 4. 4 can be written as 2 square, right? So we combine it with this omega. So it's m 2 omega square y square. And so we see that the linear harmonic oscillator oscillates with different frequencies in the x and y directions. That's why we call it an anisotropic harmonic oscillator. Okay. Alright, now once you have this, we have the frequency in the x direction and we have the frequency in the y direction. Now it's a simple matter to find the energy. It's nx plus half h cross omega and ny plus half h cross, and what's the frequency? It's 2 omega. Okay, it's twice the frequency in the x direction. Alright. Now we just now how do you calculate they have asked the excited state, all right, the first excited state. They have just asked the first excited state, but let's find the ground state, the first excited state and the second excited state. All right. So the ground state, it's simple. You just put nx equal to 0, ny equal to 0, and you see you get 3 by 2 h cross omega. Okay. So for an isotropic harmonic oscillator, if in two dimensions, all right, the first excited state would be just take nx equal to 1 and ny equal to 0, or ny equal to 0 and nx equal to 1. All right, if it's an isotropic harmonic oscillator, both these combinations would give you the same energy. Both these combinations would give you the same energy. All right, but in this case, you have to be a bit more careful. Because it has different frequencies in both directions. All right. So you will see that the next higher energy corresponds to ny equal to 0 and nx equal to 1, and not the other way about. All right. So for the first excited state, you take nx equal to 1 and ny equal to 0, and you get E is equal to 3 by 2 h cross omega plus h cross omega, which is 5 by 2 h cross omega. All right. What happens if you take ny equal to 1 and nx equal to 0? What happens now? You see that the energy goes to 7 by 2 h cross omega. All right. So the question to find the first excited state is a bit tricky here. You have to be careful to take nx equal to 1 and ny equal to 0 in this case. All right. And you see that if you take nx equal to 0 and ny equal to 1, we get a higher energy. So the degeneracy is lost here because of the anisotropy. All right. Because of this lack of symmetry, degeneracy is lost. You see that there is a connection between degeneracy and symmetry, but that is for a later discussion. All right. Okay. So this actually corresponds to the second excited state. All right. So we can say that nx comma ny is equal to 0 comma 0 is the ground state. Nx comma ny is equal to 1 comma 0 is the first excited state, and nx comma ny is equal to 0 comma 1 is the second excited state. Okay. This is a problem that was asked for one of the previous exams. Also, this degeneracy problem is asked for one of these competitive examinations. All right. Now here is one more problem. Find the expectation value of the potential energy in the end state of a harmonic oscillator. Right? Find the expectation value of the potential energy in the end state of harmonic oscillator. Right? So this is a problem that we'll do in some detail here. All right, and later on we'll be solving more problems using the same technique. So I want to clarify some of the steps here in some detail. All right, so this problem we'll do in detail. Please go through it, and then we'll be solving more problems using the same technique, using creation and annihilation operators, or using raising and lowering operators. All right, you will see that the calculation is quite simple. It doesn't involve any integrations with wave functions involving the Hermite polynomial, etc. Right. So let's look at the expectation value of the potential energy in the end state of the harmonic oscillator. Okay, so this is simply half m omega square x square, the expectation value of half m omega square x square. All right. Now we write this x in terms of the creation and annihilation operator, or the raising and the lowering operator, right? You see that you can look back at the notes. You see that x cap is square root of h cross divided by 2 m omega a plus a dagger. Okay. Similarly, you also have to remember p cap, but here we need only x cap. Now we find x cap square. All right. For x cap square, you have got this h cross by 2 m omega coming here. Right, but when you do a plus a dagger square, you have to be careful, all right, because you cannot simply write as a square plus a dagger square plus 2a dagger. This is wrong, all right, because they don't commute. You have to write a dagger and a dagger a separately. So this is a square, you have got a dagger and a dagger a plus a dagger, all right, that's also fine. Okay. Now what happens? Let's first find the expectation value of x square. In the nth state, in the nth energy eigenstate. All right. So we know the expression for the expectation value of some operator. It's simply this combination, isn't it? This is the expectation value of O. All right. So instead of psi here, we are using a general nth energy eigenstate. All right. So that's why I've written it here. This is the wave function or the state of the system here. All right. Now, one thing that you can see is that we know that these states, n energy eigenstates, are normalized. All right. So we see that we can immediately put some terms to 0. Why? Because if a dagger acts twice here, all right, forget about the normalization constant for now. If a dagger acts twice here, it will take it to n plus 2 or something, and n plus 2 with n will immediately be 0. All right. So similarly, a acting twice here will make it to n minus 1, and n minus 1 acting on n will make it to 0. All right. So you'll see that the only non-zero terms in this, are terms in which a and a dagger appear equal number of times. All right. A and a dagger are balanced. If a and a dagger are not balanced because of the normalization, orthonormality, the terms will simply disappear. So immediately we see that unbalanced term give 0. Unbalanced terms give 0. All right. So this is a technique that you can use because you don't have to carry on all these terms forever. You see immediately that both the states here are the same. All right. It's n and n. So if a and a dagger are different, appear in different numbers in a given expression, then their expectation values will definitely be 0. So this is one thing you can keep in mind. Okay. So immediately we have a simplification. We see that this is n a dagger a acting on n. All right. Now let's do it in a bit more detail. Later on we won't have to do it in so much detail because we'll remember some of these things. So this is h cross divided by 2 m omega n a dagger n plus n a dagger a n. Right. I've just split this. Right. What about this? First you apply this a dagger on n. Okay, and you see what we get here is it's square root of n plus 1 multiplied by n plus 1. Fine. Similarly, first you act this a on this, which is square root of n multiplied by get n minus 1. Fine. You just have to apply it once more. Since the square root of n plus 1 is a number, you can just pull it outside. Okay. So the square root of n plus 1 comes here, and you have got n square root of n plus 1. Again, all right, if you pull this square root of n plus 1 outside, again there is an a acting on n plus 1, all right, a acting on the state n plus 1. Okay, and what's the state a acting on state n plus 1? It's equal to n plus 1 get n, all right, so square root of n plus 1 get n, because a acting on n, we have already seen this, a acting on n is square root of n multiplied by n minus 1. Right. So here instead of n we have got n plus 1. All right. So a acting on n plus 1 is square root of n plus 1 multiplied by n minus 1. All right. And n minus 1 here is, in this case it's n plus 1 minus 1, so it is n. All right. So this gives you again a square root of n plus 1, and this n plus 1 will become n. I hope that's fine. And what happens when this, again this a square root of n I have pulled outside? What happens when a dagger acts on n minus 1? What happens when a dagger acts on n minus 1? Okay. We know that a dagger raises the value. It goes to another state n minus 1 plus 1, which is simply n. Right? And the normalization part is square root of n plus 1, which in this case is simply square root of n. All right, so we get another square root of n here. All right, this is not complicated, this is quite easy. And then you see that this is n plus 1 plus n. All right, why? Because these are numbers and n with n is 1. Simply 1. So you've got a 1 here and you've got a 1 here. So it's n plus 1 plus n. So it's h cross by 2m omega 2n plus 1. All right. We have found the expectation value of x square. We have found the expectation value of x square. All right. But we are asked here to find the expectation value of the potential energy. So you have this which is actually half m omega square x square. All right, v is equal to half m omega square x square. So we see that we already found this expectation value of x square. So this is half m omega square and h cross by 2m omega 2n plus 1. Okay, that's the result we got for expectation value of x square, and it simplifies to half h cross omega, okay, n plus half. All right, so you see that n plus half h cross omega is the total energy of the the total energy of the harmonic oscillator. It's a total harmonic oscillator energy. So the expectation value of the potential energy is half of the total energy, and you will see that the expectation value of the kinetic energy is also half of the total energy. All right. So the expectation value of the potential energy is exactly half the total energy. The other half is the kinetic energy. All right. This is a peculiarity of the harmonic oscillator. All right. So such problems can be done using creation and annihilation without any complicated integration. All right. Just imagine if you had to use the wave functions and integrate all these things, how difficult it would be. Here we have just followed a set of rules and we got a result in a very elegant manner. All right. So that's why this is a very important method. Now, again, you don't have to do so many steps because these are things you need to remember, all right? So we'll be doing more problems using this same technique. So I want you to remember these things. A dagger acting on n is square root of n plus 1, n plus 1, okay, the normalized state. Similarly, A acting on n is square root of n, n minus 1. Please remember this, all right? These are formula that you have to remember and we'll be using in the next session to solve problems. Okay, here A dagger A acting on n. All right, we said, if you remember, this is not difficult to remember because we said that A dagger A is actually n cap. Okay, A dagger A is the n cap and it simply brings out the number n. Right, that's a number operator. So this thing, it's easy to remember. You don't have to do all the calculation. If you have A dagger A acting on n, then it's n multiplied by the same n. All right, so here in this calculation, see, I've got A dagger A acting on n, right? So without this step, we could simply directly write it as n acting on n. Okay, and then we have simplified, we have gotten rid of 2 steps and you will get simply n. Okay, so expectation value of A dagger A is simply n. Okay, that's the n here. Right? Similarly, if you want, you can also remember. A dagger, the eigenvalue is n plus 1. For A dagger, the eigenvalue is n plus 1. That's something that we found out here. Right? You see that the eigenvalue for A dagger is n plus 1 because there's a square root of n plus 1 here. So that is n plus 1 multiplied by n. Okay, the ket n. So if you remember it, it's well and good. If not, you can just do one more step. All right, this you must remember. All right, A dagger A acting on n is n. Okay, because that's a number operator. Now, if you don't remember, you just do a couple of steps and you'll get this answer. All right, if you are not very sure, I mean, this is not mandatory to remember. You can just do this using this. All right, you can do this by remembering these things. All right, but if you do a few problems, you will actually automatically memorize these things. Okay, I think I should put a bracket here. All right. Now, one more thing we want you to remember is the expression for x and p in terms of A and A dagger. All right, it's x is square root of h cross by 2m omega A dagger plus A, and p is I square root of h cross m omega by 2 A dagger minus A. Right? So all other operators are often written as functions of x cap and p cap. So you can write any other operator in terms of A and A dagger if you know this thing. Okay, so if you memorize these things, there are so many problems that we can solve in a very quick and very easy way. You just have to follow certain rules, the commutation rules and some of these results. If you just remember all these things, there are many problems that we can solve quickly. All right, so we'll see more problems of this sort in the next class.